A shadow falls across the ancient floodplain. The earth trembles beneath colossal footsteps. A distant forest erupts with the panic of fleeing animals, but there is no escape, not from a predator that has ruled this land for millions of years. Its breath hisses into the dense, humid air, jaws lined with serrated blades capable of tearing flesh from bone in a heartbeat. This is not a creature of nightmares. This is history, the age when monsters were real and dominance was earned through strength, speed, and the will to survive. Dinosaurs, the unchallenged rulers of Earth for over 160 million years, an empire built on evolution, blood, and bone. What follows is a journey into their world, a catalog of truths more astonishing than fiction itself. Fact number 1. Dinosaurs first appeared during the Triassic period, approximately 230 million years ago, emerging from a lineage of archosaurs, the ruling reptiles that also gave rise to crocodiles and pterosaurs. These early dinosaurs were relatively small and bipedal, occupying a world still recovering from the catastrophic Permian-Triassic extinction event that had wiped out roughly 90% of all species. The climate was hot and dry, with vast deserts dominating the supercontinent Pangaea, and these pioneering dinosaurs initially competed with other reptilian groups for dominance in terrestrial ecosystems. Fact number 2. The evolutionary split between the two major groups of dinosaurs, Saurischia and Ornithischia, occurred early in their history and was defined by hip structure. Saurischian dinosaurs possessed a lizard-like pelvis with the pubis bone pointing forward, while Ornithischian dinosaurs had a bird-like pelvis with the pubis pointing backward. This seemingly minor anatomical difference corresponded to profound divergences in body plan, diet, and ecological roles that would play out over the next 100 million years across every continent. Fact number 3. Herrerasaurus, one of the earliest known dinosaurs from roughly 230 million years ago, exemplifies the primitive body plan from which all later dinosaurs evolved. Discovered in Argentina's Ischigualasto Formation, this carnivore measured about 3 to 6 meters in length and possessed a mix of primitive and advanced features: a flexible jaw joint for gripping struggling prey, sharp recurved teeth, grasping hands with clawed fingers, and powerful hind limbs built for pursuit. Yet it retained certain skeletal characteristics that linked it to even more ancient reptilian ancestors. Fact number 4. The Triassic-Jurassic extinction event, occurring approximately 201 million years ago, marked a turning point in dinosaur evolution by eliminating many competing reptile groups and opening ecological niches. Volcanic eruptions associated with the breakup of Pangaea released massive quantities of carbon dioxide, causing global warming, ocean acidification, and widespread habitat destruction. Dinosaurs, perhaps due to their more efficient respiratory systems or their ability to exploit varied food sources, survived this catastrophe and rapidly diversified to fill the vacant roles left by vanished competitors. Fact number 5. Sauropodomorpha, the group that would eventually include the largest land animals ever to exist, began as modest-sized omnivores and herbivores during the late Triassic. Early members like Plateosaurus reached lengths of up to 10 meters and could walk on either 2 or 4 legs, using their long necks to reach vegetation unavailable to other herbivores. These creatures possessed specialized teeth for cropping plants and gastroliths, stomach stones that aided in grinding tough plant material within their digestive systems, a feature that would persist throughout sauropod evolution. Fact number 6. The Jurassic period, spanning from 201 to 145 million years ago, witnessed the rise of the true giants among dinosaurs as sauropods evolved into colossal forms that dominated terrestrial ecosystems. Climate conditions became wetter and more equable compared to the Triassic, promoting lush vegetation and extensive forests of conifers, ferns, and cycads. These abundant plant resources supported the evolution of enormous herbivores, which in turn sustained populations of increasingly large predators, establishing the classic predator-prey dynamics that would characterize the Mesozoic era. Fact number 7. Brachiosaurus, one of the most iconic sauropods, reached estimated lengths of 26 meters and weights exceeding 50 metric tons, with extraordinarily long forelimbs that gave its body a distinctive giraffe-like slope. Its nostrils were positioned high on its skull, leading early paleontologists to mistakenly theorize it was aquatic, but modern analysis confirms it was entirely terrestrial. The creature's immense neck, containing only 13 to 14 elongated vertebrae lightened by air sacs, allowed it to browse treetops at heights of over 12 meters, a feeding strategy without parallel in modern animals. Fact number 8. The cardiovascular demands of sauropods present one of paleontology's most fascinating biomechanical puzzles. How did blood circulate from heart to brain in animals whose heads stood 6 to 9 meters above their chests? Calculations suggest that sauropod hearts must have been extraordinarily large and powerful, possibly weighing several hundred kilograms, with blood pressures far exceeding those of any living animal. Some researchers propose that auxiliary hearts or specialized valves in the neck vessels may have assisted circulation, though direct evidence for such structures remains elusive in the fossil record. Fact number 9. Allosaurus, the apex predator of the late Jurassic, exemplified the theropod body plan perfected for pursuit and combat, measuring up to 9 meters in length with a skull built to withstand tremendous impact forces. Biomechanical studies of Allosaurus skulls reveal that rather than biting and holding like modern crocodiles, this predator likely used a hatchet-like attack strategy, opening its jaws extremely wide and using powerful neck muscles to drive its upper teeth into prey, inflicting catastrophic wounds through slashing rather than crushing, an attack method suited to taking down sauropods too large to kill with conventional bites. Fact number 10. The Morrison Formation of Western North America preserves one of the most complete pictures of a Jurassic ecosystem, with fossil beds containing Allosaurus, Stegosaurus, Diplodocus, Brachiosaurus, and numerous other species. Analysis of these deposits reveals a seasonal semi-arid environment with river systems that flooded periodically, creating conditions that concentrated dinosaurs near water sources during dry periods. Many fossils show evidence of predation, scavenging, and trampling, providing direct windows into the violent interactions that characterize daily life in these ancient communities. Fact number 11. Stegosaurus, instantly recognizable by the large bony plates arranged in 2 rows along its back, raises questions about function that paleontologists continue to debate. Initially interpreted as defensive armor, the plates were actually too fragile and poorly positioned to serve this role effectively. Modern analysis suggests they functioned as thermoregulatory devices, flushed with blood to dissipate heat or absorb solar warmth, or possibly as visual displays for species recognition and mate selection, becoming more elaborate through sexual selection as individuals with more impressive plates secured better breeding opportunities. Fact number 12. The thagomizer, the tail weapon of Stegosaurus, armed with 4 large spikes, represents one of the most formidable defensive structures in the dinosaur world, capable of inflicting lethal wounds on attackers. An Allosaurus vertebra from the Morrison Formation bears a puncture wound perfectly matching the size and shape of a Stegosaurus tail spike, providing direct fossil evidence of combat between these species. The tail was powered by massive muscles and could be swung with devastating force, creating a defensive perimeter around the otherwise vulnerable hindquarters of this slow-moving herbivore. Fact number 13. Archaeopteryx, discovered in Bavarian limestone quarries and dating to approximately 150 million years ago, stands as one of paleontology's most important transitional fossils, displaying an unmistakable mosaic of reptilian and avian characteristics. It possessed teeth, clawed fingers on its wings, a long bony tail, and skeletal features, clearly linking it to small theropod dinosaurs. Yet, it also bore true feathers with the asymmetric vein structure characteristic of modern flight feathers. This creature, roughly the size of a raven, provides powerful evidence for the dinosaurian origin of birds and documents a critical stage in the evolution of powered flight. Fact number 14. The controversy surrounding Archaeopteryx' flight capabilities reflects the difficulty of reconstructing the behavior of extinct animals from skeletal remains alone. Some researchers argue that its wing structure and breastbone were too weak for sustained flapping flight, suggesting it was primarily a glider that used wings to extend leaps between trees. Others maintain that detailed analysis of its wing bones, shoulder joints, and feather attachments indicate genuine powered flight capability, though perhaps less sophisticated and energetically efficient than modern birds. The debate continues to drive research into the biomechanics and evolutionary trajectory of early avian flight. Fact number 15. The Cretaceous period, extending from 145 to 66 million years ago, saw dinosaurs reach their peak diversity, with flowering plants revolutionizing terrestrial ecosystems and providing new food sources that drove the evolution of specialized herbivores. Angiosperms appeared around 130 million years ago and rapidly diversified, creating complex forest structures with multiple canopy layers, seasonal fruits and seeds, and coevolutionary relationships with pollinating insects. These changes cascaded through food webs, supporting more diverse dinosaur communities than had existed in earlier periods, and setting the stage for some of the most spectacular creatures ever to walk the earth. Fact number 16. Spinosaurus, known from fragmentary remains discovered in Egypt and Morocco, represents one of the most bizarre and poorly understood large theropods, with recent discoveries dramatically revising understanding of its appearance and lifestyle. This creature exceeded 15 meters in length and possessed a distinctive sail or hump along its back, supported by neural spines extending up to 2 meters tall. Most remarkably, skeletal analysis reveals dense bones, similar to those of penguins and hippos, a crocodile-like snout packed with conical teeth suited for gripping fish, and proportions suggesting it spent considerable time in water, representing the only known semi-aquatic lifestyle among large dinosaurian predators. Fact number 17. The sale of Spinosaurus has generated numerous hypotheses regarding its function, from thermoregulation and fat storage to display structures for intimidating rivals or attracting mates. The sheer size and prominent position of this structure suggest visual communication played a significant role, as individuals could signal their presence and status from considerable distances. Alternatively, the sail might have functioned in a thermal capacity, helping this large predator maintain stable body temperatures while hunting in both aquatic and terrestrial environments across the varied climates of Cretaceous North Africa. Fact number 18. Carcharodontosaurus, whose name means shark-toothed lizard, was another African superpredator contemporary with Spinosaurus, reaching lengths comparable to Tyrannosaurus rex and possessing serrated teeth up to 20 centimeters long. These teeth resembled those of great white sharks in their blade-like form, designed for slicing through flesh and creating massive wounds that would cause prey to bleed out. The coexistence of Carcharodontosaurus and Spinosaurus in the same regions suggests ecological partitioning, with these apex predators likely specializing on different prey types or hunting in different habitats to minimize direct competition. Fact number 19. Giganotosaurus, discovered in Argentina and slightly larger than Tyrannosaurus rex, demonstrates that the South American continent produced its own lineage of massive predators during the Cretaceous, reaching lengths of 13 meters and weights exceeding 8 metric tons. This Carcharodontosaurid possessed a skull over 1.5 meters long, filled with serrated, blade-like teeth. Significantly, several individuals have been found in close proximity, suggesting possible pack-hunting behavior which would have allowed even the largest sauropods to be vulnerable to coordinated attacks by multiple Giganotosaurus working in concert. Fact number 20. Argentinosaurus, from the same formations as Giganotosaurus, represents the extreme end of sauropod evolution and possibly the largest land animal ever to exist, with conservative estimates placing its weight between 60 and 90 metric tons and length around 30 to 35 meters. Only fragmentary remains have been discovered, making precise size estimates challenging, but the recovered vertebrae and limb bones indicate proportions that dwarf even other giant sauropods. Supporting such mass required extraordinary adaptations in skeletal architecture, respiration, circulation, and metabolism that pushed the physical limits of terrestrial vertebrate body plans. Fact number 21. The pneumatic skeleton of sauropods, honeycombed with air sacs connected to the respiratory system, represents one of the key innovations that enabled these animals to reach such colossal sizes without collapsing under their own weight. These air-filled chambers reduced bone density by up to 75% in some elements while maintaining structural strength through complex internal bracing, similar to the construction principles of architectural trusses. This avian-style respiratory system, inherited from their archosaur ancestors, allowed sauropods to achieve dimensions impossible for mammals with their solid bone structure. Fact number 22. Titanosaurs, the most diverse and widespread group of sauropods during the Cretaceous, colonized every continent including Antarctica and evolved remarkable variations on the basic sauropod body plan. Some species like Saltosaurus developed armor plating consisting of small, bony osteoderms embedded in their skin, providing protection from predators. Others, like Repetosaurus, were relatively small by sauropod standards at only 15 meters in length. The group's success stemmed from their ability to exploit the new plant communities of the Cretaceous, including flowering plants that other herbivores struggled to process efficiently. Fact number 23. Hadrosaurs, often called duck-billed dinosaurs, represented the dominant large herbivores of late Cretaceous ecosystems across North America and Asia, evolving sophisticated dental batteries that revolutionized plant processing. These structures consisted of hundreds of tightly packed teeth arranged in multiple rows, creating grinding surfaces that continuously replaced worn teeth with new ones growing from below. This dental innovation allowed hadrosaurs to efficiently break down tough plant material, including silica-rich vegetation, that would rapidly wear down simpler tooth designs, giving them access to food sources unavailable to most other herbivores. Fact number 24. The elaborate cranial crests of Lambeosaurin hadrosaurs served as resonating chambers for producing low-frequency vocalizations that could carry for kilometers across Cretaceous landscapes, functioning as long-distance communication systems. Different species possess distinctly shaped crests, from the helmet-like structure of Corythosaurus to the tube-like extension of Parasaurolophus, each producing unique calls that would have allowed individuals to identify their own species and locate scattered herd members. Computer modeling of these structures suggests they produced sounds similar to brass instruments, filling ancient environments with haunting calls unlike anything heard in modern ecosystems. Fact number 25. Parasaurolophus, with its extraordinary tube-shaped crest extending up to 1.8 meters behind its skull, represents the extreme development of hadrosaur cranial ornamentation. The crest contained convoluted nasal passages that more than tripled the length of the airway before reaching the lungs. Acoustic analysis indicates this structure would have produced low-frequency sounds below the range of human hearing, perhaps analogous to the infrasonic communication employed by modern elephants, allowing herds to coordinate movements and warn of danger across vast distances, even in dense forest environments where visual contact was impossible. Fact number 26. The discovery of hadrosaur eggs and nesting sites in Montana's Two Medicine Formation revolutionized understanding of dinosaur parental care and social behavior. The species Maiasaura, meaning good mother lizard, built colonial nesting grounds where females returned year after year to lay eggs in circular nests spaced just far enough apart to prevent neighboring adults from trampling each other. Fossil evidence shows that hatchlings remained in nests after hatching, growing rapidly while parents brought vegetation to feed them, demonstrating a level of parental investment previously thought exclusive to birds and mammals. Fact number 27. Ceratopsians, the horned dinosaurs, evolved from small bipedal ancestors into some of the most spectacular large herbivores of the Cretaceous, characterized by their distinctive beaked faces, elaborate frills, and facial horns. The group's success in late Cretaceous North America rivaled that of hadrosaurs, with numerous species coexisting in the same regions by partitioning resources through different feeding heights and plant preferences. The enormous variety in frill shape and horn configuration across species suggests these structures functioned primarily in visual communication, species recognition, and ritualized combat rather than defense against predators. Fact number 28. Triceratops, the largest and latest evolving ceratopsian, reached lengths of 9 meters and weights exceeding 6 metric tons, with a skull accounting for nearly a third of its total body length. The 3 facial horns, 2 brow horns over 1 meter long, and a shorter nasal horn were solid bone cores sheathed in keratin, making them formidable weapons. Numerous Triceratops skulls bear scarring and partially healed injuries consistent with intraspecific combat, suggesting males engaged in ritualized battles for dominance and mating rights, locking horns, and wrestling in contests that determined hierarchy within herds. Fact number 29. The frill of Triceratops, despite its massive appearance, was solid bone in its central region, but became dangerously thin toward the edges, where it was clearly too fragile to serve as effective armor against tyrannosaur bites. Instead, this structure functioned as a display organ, richly vascularized and likely brightly colored, used in species recognition and possibly in thermoregulation. The frill could flush with blood to signal aggression, readiness to mate, or social status, while also increasing the apparent size of the animal when facing rivals or predators, similar to how modern frill-neck lizards use their expandable neck displays. Fact number 30. Tyrannosaurus rex stands as perhaps the most thoroughly studied dinosaur, known from dozens of specimens that reveal a predator exquisitely adapted for hunting the largest herbivores of its time and place. Living in western North America during the final 3 million years of the Cretaceous, this apex predator reached lengths of 12 meters and weights of 8 to 9 metric tons, with a skull approaching 2 meters in length and teeth the size of bananas. Every aspect of its anatomy was optimized for delivering and sustaining catastrophically powerful bites that could crush bone, a feeding strategy unique among large dinosaurian predators. Fact number 31. The bite force of Tyrannosaurus rex exceeded 12,000 pounds per square inch according to biomechanical modeling, roughly 3 times that of a great white shark, and powerful enough to bite through the pelvis or vertebrae of large prey animals. The teeth were not blade-like slicing instruments as in most other theropods, but rather thick, conical, and deeply rooted, designed to withstand the immense stresses of crushing bone. Coprolites attributed to Tyrannosaurus contain bone fragments up to 30 centimeters long, confirming that this animal routinely consumed skeletal elements of its prey, extracting nutrients from bone marrow unavailable to other predators. Fact number 32. The tiny forelimbs of Tyrannosaurus rex, seemingly vestigial and often mocked in popular culture, actually possessed considerable strength and may have served specific functions during feeding or mating. Each arm, though only about 1 meter long on a 12-meter animal, was heavily muscled and capable of curling over 400 pounds, with 2-fingered hands bearing sharp claws. Recent analysis suggests these limbs may have helped the animal rise from a prone position, gripped prey or mates during close encounters, or inflicted additional wounds during attacks, demonstrating that evolution retained these structures because they provided meaningful advantages. Fact number 33. Evidence increasingly suggests that Tyrannosaurus rex possessed sophisticated sensory capabilities that made it an extremely effective hunter, despite questions about whether it actively pursued living prey or scavenged carcasses. Its brain case reveals enlarged olfactory bulbs indicating an exceptional sense of smell, while the binocular vision provided by forward-facing eyes gave it better depth perception than most other theropods. The inner ear structure suggests good low-frequency hearing for detecting the footfalls of large prey at distance. Combined, these sensory systems would have made Tyrannosaurus an highly effective hunter, though, like modern apex predators, it likely scavenged opportunistically when easy meals presented themselves. Fact number 34. Growth rate studies based on bone histology reveal that Tyrannosaurus rex grew extraordinarily rapidly during adolescence, gaining approximately 2 kilograms per day during peak growth years between ages 14 and 18. Juveniles differed markedly from adults in proportions and likely behavior, with longer legs, lighter builds, and narrower skulls, suggesting they occupied different ecological niches and hunted different prey than fully grown individuals. This ontogenetic niche shifting reduced competition between age classes and allowed populations to exploit a wider range of resources, with young animals pursuing faster prey, while adults specialized on large, well-defended herbivores. Fact number 35. The question of whether tyrannosaurs possessed feathers remains contentious, with no direct evidence of integumentary structures preserved on Tyrannosaurus rex specimens, but close relatives from China showing definite feather-like coverings. Small-bodied tyrannosaurs like Utaranus, known from remarkably complete specimens, possessed filamentous protofeathers covering much of the body, likely for insulation in the cooler climates of early Cretaceous Asia. However, large adult Tyrannosaurus may have lost most body feathers due to heat dissipation challenges at gigantic size, similar to how elephants and rhinos are largely hairless compared to their smaller relatives, possibly retaining feathers only on specific body regions for display purposes. Fact number 36. Ankylosaurs represented the tank-like end of herbivore evolution, encased in extensive bony armor that made them virtually impervious to predator attacks when properly positioned. The osteoderms forming their armor were embedded in the skin and fused to underlying bone in some regions, creating a rigid shell across the back, flanks, and tail. Some species like Ankylosaurus possessed armored eyelids that could protect the eyes while maintaining vision through narrow slits. The extreme development of this defensive strategy came at the cost of mobility, making these animals slow and unable to flee, forcing them to rely entirely on their armor and weapons when threatened. Fact number 37. The tail club of Ankylosaurus consisted of several fused vertebrae forming a rigid handle that supported a massive knob of fused osteoderms, creating a biological warhammer capable of delivering devastating impacts. Biomechanical analysis indicates that a full-force swing from an adult could generate impact forces sufficient to fracture the leg bones of tyrannosaurs, potentially crippling or even killing attackers. The complex musculature controlling this weapon allowed precise aim and powerful acceleration, while the club's compact mass concentration produced maximum momentum transfer upon impact, making it one of the most formidable defensive weapons in the dinosaurian arsenal. Fact number 38. Pachycephalosaurs, the thick-headed dinosaurs, possessed dramatically thickened skull roofs composed of solid bone, up to 25 centimeters thick in the largest species, leading to hypotheses about head-butting behavior similar to modern bighorn sheep. However, finite element analysis of these skulls reveals they were poorly suited for direct high-impact collisions, as the stresses would likely have caused severe injury to the brain and neck. Alternative theories suggest males engaged in flank-butting contests where opponents struck each other's sides rather than heads directly, or used their domed skulls in pushing matches that determined dominance without risking catastrophic injury. Fact number 39. Therizinosaurus, among the strangest dinosaurs ever discovered, possessed the longest claws of any known animal, with forelimb claws extending over 1 meter in length and measuring only slightly curved and relatively narrow. Initially, paleontologists misidentified these claws as belonging to a giant turtle-like reptile, as they seemed too bizarre to belong to a theropod dinosaur. Subsequent discoveries revealed Therizinosaurus was indeed a theropod, but one that had abandoned carnivory entirely in favor of herbivory, using its enormous claws to pull down branches and strip leaves from trees, while also potentially defending against predators, including tyrannosaurs, with which it shared its Mongolian ecosystem. Fact number 40. The oviraptorosaurs, close relatives of birds, displayed remarkable cranial diversity and likely occupied varied ecological niches in late Cretaceous Asian ecosystems. Many species possessed elaborate casques and crests formed from fused nasal and premaxillary bones, structures that probably functioned in visual display and species recognition. The name egg thief lizard derives from the initial discovery of an oviraptor specimen atop a nest of eggs, initially interpreted as a predator caught in the act of raiding. Subsequent discoveries revealed these were actually the animal's own eggs. Preserved while brooding, the parent had died protecting its clutch, providing direct evidence of avian-like parental care in non-avian dinosaurs. Fact number 41. Deinonychus, discovered by paleontologist John Ostrom in the 1960s, revolutionized scientific understanding of dinosaurs by demonstrating that some species were active, agile predators, rather than the sluggish reptilian creatures previously imagined. This wolf-sized theropod possessed an enlarged, sickle-shaped claw on each foot, held off the ground while running and deployed in attacks to grip and slash prey. The discovery of multiple Deinonychus individuals associated with a single Tenontosaurus skeleton suggested possible pack-hunting behavior, implying complex social interactions and coordinated strategies that required intelligence and communication far beyond what was attributed to dinosaurs before Ostrom's groundbreaking work. Fact number 42. The famous sickle claw of dromaeosaurs, like Deinonychus and Velociraptor, was long interpreted as a slashing weapon used to disembowel prey, but biomechanical testing suggests a different function. The claw's curvature and robustness indicate it was better suited for piercing and gripping rather than slicing, similar to the talons of modern raptorial birds. Predation likely involved leaping onto prey, using the claws to secure attachment while the animal was too large to shake the predator loose, then using tooth-filled jaws and forelimb claws to inflict numerous smaller wounds that eventually caused death through blood loss and shock, rather than a single, slashing, disemboweling strike. Fact number 43. Velociraptor, despite its outsized fame from popular culture, was actually a relatively small predator about the size of a turkey, standing roughly half a meter tall at the hip and measuring 2 meters in total length, including its long, stiff tail. The animal lived in the deserts of late Cretaceous Mongolia rather than the lush forests depicted in films, hunting smaller dinosaurs, early mammals, and possibly scavenging when opportunities arose. Most dramatically, one spectacular fossil from Mongolia preserves a velociraptor locked in mortal combat with a protoceratops, the predator's sickle claw embedded in the herbivore's throat, while the protoceratops's beak grips the velociraptor's arm, both animals apparently buried suddenly by a collapsing sand dune during their struggle. Fact number 44. Feathered dinosaur fossils from early Cretaceous deposits in Liaoning Province, China, have transformed understanding of dinosaur appearance and the evolution of feathers and flight. Species like Microraptor possessed 4 wings with long flight feathers on both forelimbs and hind limbs, creating a biplane-like configuration unlike any living animal. These feathers were not the brown or gray colors often depicted, but instead showed evidence of iridescent black coloration, similar to modern crows and grackles, determined through analysis of melanosomes, microscopic pigment-containing structures preserved in the fossil feathers. This indicates dinosaurs displayed sophisticated coloration for communication and display, just as modern birds do. Fact number 45. Yutyrannus, a tyrannosaur from early Cretaceous China, represents the largest definitely feathered dinosaur known to science, reaching lengths of 9 meters and weights exceeding 1 metric ton. The preserved integument shows extensive filamentous feather-like coverings across the body, including relatively long feathers, up to 15 centimeters in length. This discovery confirmed that feathers were not restricted to small dinosaurs, but appeared even in large predators, though, as mentioned earlier, the absence of feather evidence on Tyrannosaurus rex suggests truly gigantic tyrannosaurs in warmer climates may have reduced their feather covering to manage heat dissipation challenges that come with massive body size. Fact number 46. Sinosauropteryx, the first non-avian dinosaur discovered with preserved integument, displayed a coat of simple filamentous proto-feathers covering its entire body when it was described in 1996. Later analysis revealed even more remarkable details. The tail displayed alternating dark and light bands, creating a striped pattern, and the face showed countershading, darker coloration on top, grading to lighter underneath. This distribution of color helps conceal three-dimensional form by counteracting the effects of shadows, a camouflage technique employed by many modern animals, indicating that even small predatory dinosaurs faced sufficient predation pressure or needed to avoid detection by prey. That natural selection favored cryptic coloration. Fact number 47. The extinction of non-avian dinosaurs. 66 million years ago resulted from the impact of an asteroid approximately 10 to 15 kilometers in diameter, striking the Yucatan Peninsula in what is now Mexico, creating the Chicxulub crater, 180 kilometers across. The impact released energy equivalent to billions of nuclear weapons, instantly vaporizing rock and ejecting trillions of tons of material into the atmosphere. The immediate blast zone, extending hundreds of kilometers, was incinerated, while global wildfires ignited by raining ejecta-burned vast regions of the planet. Tsunamis, hundreds of meters high, devastated coastlines, and the atmosphere filled with dust and aerosols that blocked sunlight for months to years, collapsing photosynthesis and triggering ecosystem collapse from the bottom up. Fact number 48. The aftermath of the Chicxulub impact plunged Earth into an impact winter where darkness and cold prevailed for potentially a year or longer, followed by rapid greenhouse warming as the dust settled, but carbon dioxide and other greenhouse gases remained in the atmosphere. Plants died across the globe, eliminating the food base for herbivores, which in turn starved the predators. Animals dependent on photosynthetic primary productivity, especially large animals with high food requirements, suffered extinction at catastrophically high rates. The asteroid struck at a particularly vulnerable time in Earth's history, when volcanic eruptions in India's Deccan Traps were already stressing ecosystems with climate fluctuations and possibly creating conditions where ecosystems had little resilience to absorb additional shocks. Fact number 49. Non-avian dinosaur fossils have never been found in undisputed rock layers above the Cretaceous-Paleogene boundary, confirming that these animals did not survive the extinction event except through their avian descendants. However, the extinction was selective rather than absolute. While large dinosaurs perished, smaller animals, including early mammals, crocodilians, champsosaurs, many lizards and snakes, and numerous bird lineages survived, suggesting that small body size, ability to shelter underground or underwater, and omnivorous or detritivorous diets conferred advantages during the extinction crisis. The world that emerged was radically different, with mammals rapidly diversifying to fill niches formerly occupied by dinosaurs in one of evolution's most dramatic adaptive radiations. Fact number 50. Birds represent the direct descendants of small carnivorous theropod dinosaurs, specifically nested within the Maniraptoran group that includes dromaeosaurs and oviraptorosaurs, making them literally living dinosaurs by modern phylogenetic classification standards. The transition from non-avian dinosaurs to birds involved not a sudden transformation, but gradual accumulation of avian characteristics over tens of millions of years. Feathers appeared first for insulation and display, then were modified for flight. Bones became increasingly pneumatic and lightweight. The tail shortened and stiffened, the hand bones fused, and the flight stroke evolved through a series of intermediate forms. Living birds retain numerous dinosaurian features, including scales on their legs, similar skull kinesis patterns, and the basic archosaurian respiratory system with air sacs extending into bones. Fact number 51. The discovery of exceptionally preserved dinosaur specimens in recent decades has revealed soft tissue details that bring these ancient animals vividly to life in ways impossible from bones alone. Fossilized skin impressions show that while many dinosaurs possessed scales similar to modern reptiles, these scales varied dramatically in size, shape, and arrangement across the body and between species. Some regions displayed tubercles, larger bony protrusions embedded in the skin, while other areas had small pebble-like scales or smooth skin. In feathered species, the integument varied from simple filaments to complex pennaceous feathers, identical in structure to those of modern birds, demonstrating that dinosaur appearance was far more diverse than early reconstructions suggested. Fact number 52. Melanosomes, the microscopic organelles that contain pigments in feathers, skin, and hair, occasionally preserve in exceptionally fossilized specimens, allowing paleontologists to reconstruct actual colors of dinosaurs with scientific rigor rather than artistic speculation. Different melanosome shapes correspond to specific colors. Elongate melanosomes produce black and gray tones, spherical ones produce reddish-brown colors, and the absence of melanosomes suggests white or pale coloration. By mapping melanosome distributions across feathered dinosaur fossils, researchers have reconstructed color patterns in species like Anchiornis, revealing a creature with black and white wings, a reddish face and crest, and striped legs, a specific, empirically determined color scheme rather than imaginative guesswork. Fact number 53. Coprolites, fossilized feces, provide direct evidence of dinosaur diet and digestive physiology, preserving actual consumed food items rather than inferring diet from tooth shape alone. Large coprolites attributed to Tyrannosaurus contain crushed bone fragments demonstrating bone-crushing feeding behavior, while hadrosaur coprolites contain finely comminuted plant material showing the effectiveness of their dental batteries at processing vegetation. Some coprolites preserve pollen, seeds, and wood fragments that indicate specific plant species consumed, occasionally including plants not obviously suited for dinosaur consumption by modern standards. Parasitic worm eggs found in some coprolites even reveal that dinosaurs suffered from intestinal parasites just as modern animals do. Fact number 54. Trackways and footprints, far more common in the fossil record than skeletal remains, provide unique information about dinosaur locomotion, behavior, speed, and ecology unavailable from bones. Tracks preserve stride length, foot pressure distribution, walking speed, and whether the animal was moving individually or in groups. Sauropod trackways from various locations show these giants often traveled in herds with juveniles positioned toward the center of the group, surrounded by protective adults. Theropod tracks occasionally show evidence of pursuit, with footprints indicating increasing stride length suggestive of acceleration. In rare cases, trackways preserve the exact moment of interaction between species, such as a predator approaching potential prey, documenting behaviors impossible to infer from skeletal material. Fact number 55. The largest dinosaur footprints ever discovered measure over 1 meter in diameter and represent the passage of gigantic tanosaurs through muddy substrates that preserved their impressions for millions of years. Some trackways in South America and Australia extend for hundreds of meters, documenting the migrations of sauropod herds across ancient floodplains. The depth of these footprints, sometimes exceeding half a meter, indicates the tremendous weight these animals placed on relatively small feet, generating ground pressures that modern elephants approach but do not exceed. Analysis of footprint depth variation between fore and hind feet confirms that sauropods carried most of their weight on their hind limbs, with the forelimbs serving more to stabilize and steer than to support mass. Fact number 56. Evidence of dinosaur social behavior extends beyond trackways to bone beds containing numerous individuals of the same species, suggesting these animals sometimes congregated in large groups. The Calophysis Quarry at Ghost Ranch, New Mexico, contains remains of hundreds of individuals buried together, possibly killed by a flash flood while gathering near water during a drought. Similar mass accumulations of ceratopsians, hadrosaurs, and other herbivores indicate herding was common among plant-eating dinosaurs, likely providing protection through numbers against predators. However, interpreting these deposits requires caution, as some mass accumulations may result from attritional death over time near water sources rather than catastrophic burial of actual herds. Fact number 57. The respiratory system of dinosaurs, inherited from archosaur ancestors, utilized air sacs that extended from the lungs into the body cavity and even pneumatized many bones, creating a unidirectional airflow pattern fundamentally different from the bidirectional breathing of mammals. In this system, air flows through the lungs in one direction continuously during both inhalation and exhalation, allowing more efficient oxygen extraction than mammalian lungs achieve. This respiratory adaptation explains how sauropods could maintain the metabolic rates necessary to support their enormous bodies, and how theropods could sustain the energetic demands of active predation, giving dinosaurs significant physiological advantages over contemporary mammalian competitors. Fact number 58. The pneumatic vertebrae and limb bones of many dinosaurs, especially sauropods and theropods, contained extensive systems of air-filled chambers connected to the respiratory system, drastically reducing skeletal weight without compromising strength. Some sauropod vertebrae were up to 80% air by volume, with the remaining bone organized into complex structural supports similar to the internal architecture of aircraft wings or architectural trusses. This weight-saving strategy was essential for enabling the evolution of gigantic body sizes, as a sauropod with solid bones would have required disproportionately thick leg bones to support its weight, creating a positive feedback loop where adding bone mass to support weight simply required more support bones, quickly reaching a biomechanical impossibility. Fact number 59. Dinosaur metabolism remains one of the most debated topics in paleontology, with evidence suggesting these animals did not fit neatly into categories of cold-blooded ectothermy or warm-blooded endothermy like modern reptiles and mammals. Bone histology showing rapid growth rates, predator-prey ratios consistent with high metabolic rates, and evidence of sustained activity levels all suggest elevated metabolism compared to modern reptiles. However, the enormous sizes reached by sauropods would have created thermal inertia effects where sheer mass made them functionally homeothermic, maintaining stable body temperatures, regardless of metabolic rate. The current consensus favors mesothermy, an intermediate state where metabolic rates exceeded reptilian levels but remained below full avian or mammalian endothermy. Fact number 60. The discovery that many theropod dinosaurs, particularly smaller species, possessed feathers has forced reconsideration of their thermoregulatory physiology, as feathers primarily function for insulation in modern animals, suggesting their original bearers needed to retain metabolically generated heat. Small feathered dinosaurs would have lost heat rapidly due to their high surface area to volume ratios without elevated metabolic rates to generate replacement heat, implying that at least these species maintained relatively high resting metabolic rates. However, the lack of feathers on large-bodied dinosaurs in hot climates suggests that thermal constraints varied dramatically with body size and environmental temperature, producing a range of thermoregulatory strategies across the diverse array of dinosaurian forms. Fact number 61. Growth patterns preserved in dinosaur bone histology reveal that these animals typically grew rapidly to adult size over a period of decades. Then growth slowed dramatically or ceased, creating distinct marks in the bone similar to tree rings. These growth lines, called lines of arrested growth or LAGs, allow researchers to determine age at death and construct growth curves showing how fast individuals of different species matured. Large theropods like Tyrannosaurus reached sexual maturity around 15 to 18 years of age and lived into their 20s or early 30s at most. Sauropods continued growing throughout life, but reached functional adult size in their 20s, with some individuals possibly living 50 to 80 years or even longer. Fact number 62. Sexual dimorphism in dinosaurs remains difficult to confirm from skeletal material, as many supposed cases of different forms within one species may actually represent distinct species or different growth stages. However, some cases appear robust. Certain specimens of Tyrannosaurus possess distinctively wider pelvic canals, potentially indicating females adapted for passing large eggs. Among ceratopsians and pachycephalosaurs, variation in frill or dome size may reflect male-female differences or might instead represent age classes. The discovery of medullary bone, a specialized tissue in modern female birds that stores calcium for eggshell formation, in a Tyrannosaurus femur, provides definitive evidence that this individual was a reproductively active female, offering a tool for potentially sexing other specimens. Fact number 63. The reproductive biology of dinosaurs remains poorly understood due to the scarcity of preserved eggs, embryos, and nesting sites, but available evidence suggests considerable diversity in reproductive strategies. Egg shapes ranged from spherical to highly elongate, with shell textures varying from smooth to highly ornamented. Clutch sizes varied from just a few eggs in some species to 30 or more in others. Some species like Maiasaura apparently provided extensive parental care, with adults feeding hatchlings in the nest, while others like sauropods seem to have laid eggs and then provided minimal or no parental investment, relying on high fecundity and rapid growth to ensure offspring survival despite high mortality rates. Fact number 64. The eggs of large dinosaurs presented a biomechanical constraint on size evolution, as eggshells must be thick enough to support the weight of overlying eggs and the sitting parent, yet thin enough for the embryo to break through when hatching. This created an upper limit on egg size of about 5 liters and masses around 5 kilograms, meaning that even the largest dinosaurs weighing 50 tons or more hatched from eggs smaller than a soccer ball. This extreme difference between hatchling and adult size created radical shifts in ecology and behavior over an individual's lifetime, with juvenile and adult members of the same species occupying entirely different ecological niches and potentially barely recognizable as the same species based on proportions and capabilities. Fact number 65. The smallest dinosaurs known include hummingbird-sized species from the Mesozoic that pushed the lower size limits for actively flying animals. Microraptor, despite being four-winged and about the size of a crow, was far from the smallest dinosaur. The smallest non-avian dinosaur currently known is probably Parvicursor, a tiny alvarezsaurid about 39 centimeters long and weighing perhaps 150 grams. However, early birds from the Mesozoic included species comparable in size to modern hummingbirds, measuring just a few centimeters in body length. These tiny dinosaurs occupied ecological niches as insectivores, using their small size to access food resources unavailable to larger species and likely possessing metabolic rates comparable to modern small birds. Fact number 66. Alvarezsaurids represent one of the most bizarre branches of theropod evolution, characterized by robust but extremely short forelimbs ending in a single huge claw, leading to extensive debate about their lifestyle and feeding ecology. Initially, some paleontologists suggested these claws were used to tear open termite mounds, similar to modern anteaters, while others proposed they dug for underground prey or stripped bark from trees. The discovery of better preserved specimens showed that these animals had features suggesting insectivory, including teeth reduced to small pegs, suitable for grasping insects rather than tearing flesh. Whatever their precise ecology, alvarezsaurids demonstrate that theropods evolved into ecological niches far removed from the typical predator body plan. Fact number 67. Ornithomimids, the ostrich dinosaurs, converged on a body plan remarkably similar to modern flightless birds, with small heads, toothless beaks, long flexible necks, compact bodies, and extremely long legs built for speed. Some species like Dinocheirus reached enormous sizes, measuring 11 meters long and standing several meters tall, representing some of the largest bipedal animals ever to exist. Initially known only from massive forelimbs with huge claws, Dinocheirus remained mysterious for decades, until complete skeletons revealed a creature with a humped back, possibly supporting fatty tissue or a muscular ridge, and a broad duck-like snout, suggesting it fed on aquatic vegetation and small animals in wetland environments. Fact number 68. The evolution of herbivory from carnivorous ancestors occurred multiple times independently within theropod dinosaurs, demonstrating evolutionary plasticity in this group. Therizinosaurs, oviraptorosaurs, ornithomimids, and several other lineages abandoned meat-eating in favor of plant consumption, developing specialized adaptations including leaf-shaped teeth, powerful jaw muscles, elongated necks for browsing, and massive guts for fermenting plant material. This repeated evolution of herbivory suggests strong ecological pressure and opportunity for theropods to exploit plant resources, perhaps driven by competition among carnivores or the abundance of vegetation in Mesozoic ecosystems. Each lineage evolved unique solutions to the challenges of plant eating, creating remarkable diversity in herbivorous theropod body plans. Fact number 69. Spinosaurids represent another case of dramatic ecological divergence among theropods, abandoning terrestrial predation to become specialized fish eaters, occupying semi-aquatic niches. Beyond Spinosaurus itself, the family includes Baryonyx and Suchomimus, both possessing similar adaptations: elongate crocodile-like snouts, conical teeth for gripping slippery prey, reduced hip and hind limb proportions, and enlarged forelimb claws, possibly used to hook fish from water. Isotopic analysis of spinosaurid teeth indicates they consumed substantial amounts of aquatic prey, confirming inferences from anatomy. These animals demonstrate that even among large theropods, traditionally viewed as apex terrestrial predators, ecological specialization could produce forms radically different from the standard tyrannosaur or allosaur template. Fact number 70. The arms race between herbivorous dinosaurs and the plants they consumed drove extensive coevolution throughout the Mesozoic, with plants evolving defensive adaptations including tough fibrous tissues, silica-rich leaves that rapidly wore down teeth, toxic chemical compounds, and physical defenses like thorns and spines. Herbivorous dinosaurs responded with increasingly sophisticated dental batteries, powerful jaw muscles, massive gut capacity for processing low-quality forage, and possibly symbiotic gut bacteria for breaking down cellulose and detoxifying plant defensive compounds. The evolution of flowering plants in the Cretaceous represented a major shift in this dynamic, as angiosperms grew rapidly and recovered quickly from herbivory, potentially allowing them to tolerate intensive browsing better than gymnosperms and ferns. Fact number 71. Gut contents and coprolites occasionally preserve direct evidence of dinosaur diets that confirms or contradicts inferences from tooth morphology. A Compsognathus specimen contains the skeleton of a small lizard in its abdominal region, documenting this small predator's diet. A baryonyx fossil includes partially digested fish scales and bones, confirming piscivory. Some ornithomimid remains contain gastroliths along with plant material, indicating herbivory despite these animals' theropod ancestry. Perhaps most remarkably, some dinosaur coprolites contain fragments of rotten wood heavily perforated by insect borings, suggesting the dinosaurs were consuming wood not for nutrition, but to harvest the protein-rich insect larvae living within it, demonstrating unexpectedly complex foraging behavior. Fact number 72. The biomechanics of sauropod necks presents fascinating engineering challenges, as these structures reach lengths of up to 15 meters in species like Mamenchisaurus, while supporting a head and providing sufficient strength and mobility for feeding. The vertebrae were extensively pneumatized and lengthened, with neural spines and cervical ribs providing attachment points for massive ligaments and muscles. Some research suggests sauropods could not raise their necks far above shoulder height due to blood pressure and structural constraints, while other analyses indicate vertical neck postures were achievable. The truth probably varied among species, with some specialized for high browsing and others for sweeping their necks horizontally across broad feeding zones, reducing the energy cost of locomotion while feeding. Fact number 73. Evidence of dinosaur diseases and injuries preserved in fossil bones reveals that these animals suffered from many of the same pathologies affecting modern vertebrates, including arthritis, infections, tumors, and traumatic injuries. Tyrannosaur skeletons frequently show healed bite marks from conspecific combat, with some individuals bearing multiple severe injuries that nonetheless healed, indicating these animals possessed robust immune systems and could survive devastating wounds. Some specimens show evidence of gout, a metabolic disease caused by uric acid crystallization in joints. Bone infections called osteomyelitis appear in various species, sometimes spreading through entire limbs. These pathologies provide glimpses into the daily hazards and health challenges dinosaurs faced throughout their lives. Fact number 74. The longest dinosaur ever discovered, Supersaurus, reached estimated lengths approaching 34 meters from nose to tail tip, though it was less massive than shorter but bulkier sauropods like Argentinosaurus. Most of this length consisted of an extraordinarily elongate neck and tail, with the body proper similar in size to other large sauropods. Such extreme elongation served to maximize feeding reach while minimizing the energetic cost of locomotion, allowing the animal to access vegetation across a wide area without moving its massive body. However, these proportions came at the cost of agility and speed, rendering these animals vulnerable to predators if caught far from their herds or in terrain where their superior reach provided no advantage. Fact number 75. The question of whether dinosaurs were capable of complex cognition and sophisticated behavior depends partly on estimating brain size relative to body size, a measure called the encephalization quotient. Most dinosaurs had relatively small brains compared to mammals of similar body size, with large sauropods possessing brains weighing only a few hundred grams, despite body masses of tens of tons. However, some small theropods, particularly dromaeosaurs and troodontids, had encephalization quotients approaching those of modern birds, suggesting considerable cognitive capacity. Brain size alone provides limited insight into actual behavioral complexity, as modern birds demonstrate sophisticated behaviors, including tool use, problem-solving, and complex social interactions, despite having small brains by mammalian standards. Fact number 76. Troodon, often cited as among the most intelligent non-avian dinosaurs based on its relatively large brain and stereoscopic vision, possessed a brain roughly comparable in relative size to modern emus and ostriches, suggesting cognitive capabilities at least equivalent to these birds. Its large eyes with forward-facing orientation provided excellent depth perception useful for hunting in dim light conditions, possibly indicating nocturnal or crepuscular activity patterns. The combination of reasonable intelligence, good vision, grasping hands, and potentially complex social behavior would have made Troodon an formidable predator of small prey, despite its relatively modest size of about 2 meters in length and 12 kilograms in mass. Fact number 77. The preservation of dinosaur soft tissues, once considered impossible, has been documented in several specimens where collagen, blood vessels, and possibly even DNA fragments have been isolated from bone fossils, though these findings remain controversial and difficult to replicate. Mary Schweitzer's discovery of flexible blood vessels and organic matrix in Tyrannosaurus bone shocked the paleontological community and suggested that under exceptional circumstances, organic molecules might survive much longer than previously thought possible. However, claims of viable DNA preservation remain highly skeptical, as DNA degrades relatively rapidly and is unlikely to remain intact over tens of millions of years. Any recovered genetic material would be fragmentary and heavily damaged, making the science fiction scenario of cloning dinosaurs from ancient DNA essentially impossible with current or foreseeable technology. Fact number 78. The distribution of dinosaurs across Mesozoic continents reveals that while these animals achieved global distribution, significant faunal differences existed between regions due to geographic barriers and vicariance, as Pangaea fragmented into separate landmasses. North America and Asia maintained periodic land connections allowing faunal exchange, resulting in similar dinosaur assemblages including tyrannosaurs, ceratopsians, and hadrosaurs. South America, increasingly isolated after the Cretaceous breakup of Gondwana, developed distinctive dinosaur faunas, including abelosaurid predators and unique sauropod lineages. The island continent of Europe during the late Cretaceous featured dwarf dinosaurs that had undergone insular dwarfism, evolving smaller body sizes in response to limited resources on islands. Fact number 79. Insular dwarfism affected dinosaurs in the same way it impacts modern large mammals on islands, with late Cretaceous European dinosaurs including dwarf sauropods, small ornithopods, and reduced-size predators compared to their mainland relatives. Magyarosaurus, a dwarf titanosaur from Romania, reached only 6 meters in length, despite belonging to a group that typically exceeded 20 meters. These dwarf species evolved on the island archipelago that comprised Europe during the late Cretaceous, when high sea levels flooded lowland areas and isolated populations on scattered islands. Limited food resources and reduced predation pressure on islands select for smaller body sizes, demonstrating that the same ecological principles governing modern fauna applied equally to dinosaur populations. Fact number 80. The debate over dinosaur posture and locomotion has evolved dramatically since the 19th century, when dinosaurs were reconstructed as tail-dragging, slow-moving, quasi-aquatic creatures. Modern understanding recognizes that dinosaurs held their tails elevated off the ground, using them as counterbalances, and were fundamentally terrestrial and often quite agile. Large theropods like Tyrannosaurus could probably achieve running speeds of approximately 17 to 25 miles per hour in short bursts, though their immense mass made sustained running dangerous due to the risk of catastrophic falls. Smaller theropods were considerably more agile, while many large herbivores relied on mass and defensive weapons rather than speed to deter predators. Fact number 81. Trackway evidence sometimes preserves the only record of dinosaur behaviors that leave no trace in skeletal remains, including swimming behavior in several dinosaur groups. Some trackways show only forelimb impressions, suggesting the animals were swimming with their hind limbs and using forelimbs to push off the bottom in shallow water. Other tracks show the transition from terrestrial walking into swimming and back to walking as animals crossed channels. These traces demonstrate that at least some dinosaurs, particularly hadrosaurs and sauropods, were competent swimmers when necessary, though whether any species were primarily aquatic remains doubtful, given the numerous anatomical features clearly adapted for terrestrial life. Fact number 82. The discovery of melanin and other pigments in fossil feathers has extended to analyzing fossilized scales and skin, occasionally preserving evidence of color patterns in non-feathered dinosaurs. A Psittacosaurus specimen from China with exceptional skin preservation shows counter-shading color patterns, dark on top and light below, similar to many modern animals that use this coloration to reduce apparent three-dimensionality and help conceal themselves from predators or prey. The tail displays alternating dark and light stripes, perhaps providing disrupted coloration that broke up the body outline. These findings indicate that even large herbivorous dinosaurs employed camouflage strategies, suggesting that predation pressure remained significant throughout the lives of these animals. Fact number 83. The coexistence of numerous large predator species in some dinosaur ecosystems seems paradoxical, as modern terrestrial ecosystems typically support only one or two large predator species due to energetic constraints. Yet, late Cretaceous North America hosted Tyrannosaurus, Albertosaurus, Troodon, and several other carnivorous dinosaurs simultaneously. This apparent paradox resolves through niche partitioning based on prey size preferences and ontogenetic niche shifts, where juvenile and adult members of the same predator species hunted different prey. Young Tyrannosaurus, for instance, had different proportions and capabilities than adults, and likely pursued smaller, faster prey, reducing competition with adult conspecifics and allowing the same species to exploit a wider range of prey across the predator's lifespan. Fact number 84. Evidence of cannibalism has been documented in several dinosaur species, most notably in Majungasaurus, an abelisaurid theropod from Madagascar. Numerous Majungasaurus bones bear tooth marks precisely matching the teeth of other Majungasaurus individuals, indicating these animals fed on members of their own species. Whether this resulted from active predation, possibly related to combat between rivals, or opportunistic scavenging of already dead individuals, remains unclear. Allosaurus similarly shows evidence of cannibalism, with tooth-marked bones consistent with conspecific feeding. In environments where large prey animals were scarce, or where combat between rivals resulted in deaths, cannibalism may have represented an important supplementary food source. Fact number 85. The relationship between body size and species diversity in dinosaurs reveals interesting patterns, with small-bodied dinosaur species significantly underrepresented in the fossil record compared to large-bodied forms, likely reflecting preservation bias rather than true rarity. Small animals have more fragile skeletons that are less likely to fossilize and survive to discovery, and they occupy smaller home ranges, reducing geographic distribution and discovery probability. Statistical analyses attempting to correct for this bias suggest that small dinosaurs were considerably more diverse than large species, forming the majority of dinosaur diversity, similar to modern mammalian faunas, where small species vastly outnumber large ones. This implies our understanding of dinosaur ecology remains incomplete, missing significant components of these ancient ecosystems. Fact number 86. The evolution of powered flight represents one of the most significant transitions in vertebrate history, and dinosaurs achieved this breakthrough at least twice independently. Once in the lineage leading to birds, and possibly once or more times in non-avian paravians like Scansoriopterygids. Scansoriopterygids possessed elongate fingers supporting wing membranes similar to bats, rather than feathered wings, representing a completely different solution to the challenge of flight. However, these membrane-winged dinosaurs appear to have been evolutionary dead ends, leaving no descendants, while feathered flight evolved into the extraordinary diversity of modern birds. The reasons feathered wings proved superior to membrane wings in dinosaurs remain debated, but may relate to durability, repairability, and the multifunctional nature of feathers. Fact number 87. The dinosaur-bird transition involved not just the evolution of flight, but radical changes in reproductive biology, including the evolution of hard-shelled eggs, extended parental care, and eventually adaptations related to powered flight such as sequential molting patterns and specialized brooding behaviors. The retention of only a single functional ovary in most birds, the left one, reducing weight for flight, appears in some non-avian paravians as well, suggesting this adaptation preceded true powered flight. The evolution of brooding, where parents sit on eggs to maintain elevated temperatures for development, is documented in numerous non-avian dinosaurs through fossils of adults preserved atop nests, indicating this behavior characterized many maniraptoran lineages and was not unique to birds. Fact number 88. The climate of the Mesozoic differed dramatically from modern conditions, with no permanent ice caps, much higher sea levels, and generally warmer temperatures extending to high latitudes. During the Cretaceous, dinosaurs inhabited polar regions where they experienced months of winter darkness and temperatures that, while mild by modern polar standards, still included freezing conditions. The discovery of dinosaur fossils in Alaska, Australia, and Antarctica demonstrates these animals successfully colonized high-latitude environments despite the challenges of seasonal light regimes and cooler temperatures. How they managed these conditions remains debated. Some may have migrated seasonally toward lower latitudes, while others apparently remained year-round, possibly entering torpor during harsh winter months or maintaining high metabolic rates through the cold season. Fact number 89. The biomechanics of ceratopsian frills extend beyond their role in display to questions about locomotion and head mobility, as these structures added considerable weight and changed the center of mass of the head. Large frills in species like Triceratops and Pentaceratops required powerful neck muscles to support and maneuver, with muscle attachment sites on the skull and vertebrae showing extraordinary development. The weight and forward projection of the skull created significant moments during locomotion that the neck muscles had to constantly counteract, raising questions about how these animals distributed their mass during activities like feeding, drinking, or combat. The answer lies partially in the tripod-like stance adopted during head lowering, where the horns and beak formed contact points that supported the skull's weight while the animal browsed on low vegetation. Fact number 90. Sexual selection likely drove the evolution of many elaborate cranial structures in dinosaurs, including the crests of hadrosaurs, the horns and frills of ceratopsians, and the domes of pachycephalosaurs, through runaway selection where exaggerated ornaments became indicators of individual quality. In modern animals, costly ornaments serve as honest signals of bearer fitness, as only healthy individuals can afford to invest resources in elaborate structures while still maintaining body condition and immune function. The same principle probably applied to dinosaur ornamentation, with individuals bearing larger, more symmetrical, or more colorful crests, horns, or frills, signaling superior genetic quality and health status to potential mates, driving the evolution of increasingly elaborate structures even when they provided no survival advantage and potentially imposed costs through increased weight or visibility to predators. Fact number 91. The question of whether dinosaurs were capable of complex vocalizations has been addressed through analysis of hyoid bones, syrinx structures in birds, and modeling of vocal tracts based on skull shape. Modern birds produce sounds using a syrinx, a specialized organ located where the trachea branches into bronchi, and evidence of syrinx-like structures has been found in some fossil birds from the Mesozoic. However, non-avian dinosaurs lack definitive evidence of syringes, suggesting they produced sounds differently, perhaps using their throats and nasal passages, or using closed-mouth vocalizations where sounds resonate in inflatable air sacs rather than being produced in an open mouth. The elaborate crests of hadrosaurs functioned as resonating chambers, implying these dinosaurs produced low-frequency calls, while other species may have relied more on visual displays or chemical signals for communication. Fact number 92. Evidence of dinosaur hearing comes from the structure of the inner ear, particularly the cochlea in birds and the equivalent structures in non-avian dinosaurs. CT scanning of dinosaur skulls allows reconstruction of the inner ear and estimation of the frequency ranges these animals could detect. Large theropods like Tyrannosaurus had inner ears suggesting sensitivity to low-frequency sounds, useful for detecting the footfalls of large prey or the calls of conspecifics over long distances. Small dinosaurs showed sensitivity to higher frequencies, appropriate for detecting insect sounds or the calls of similarly small animals. The semicircular canals of the inner ear, responsible for balance, indicate that agile predators had more sensitive balance systems than slower-moving herbivores, as expected from their different locomotor demands. Fact number 93. The evolution of toothlessness and beaks occurred multiple times independently in dinosaurs, appearing in ornithomimids, oviraptorosaurs, therizinosaurs, and ultimately characterizing all modern birds. Beaks offer several advantages over teeth. They grow continuously, eliminating the need to replace worn teeth. They're lighter than tooth-bearing jaws, reducing head weight, and they allow more varied food manipulation, including cracking seeds, stripping leaves, and probing in soil or water. However, beaks require different feeding strategies than teeth, often relying on gastroliths to grind food in a muscular gizzard rather than chewing with teeth. The repeated evolution of beaks suggests strong selection for these structures in herbivorous and omnivorous theropods, though carnivorous theropods generally retain teeth throughout their evolutionary history. Fact number 94. The largest flying animals of all time were not dinosaurs, but pterosaurs, the flying reptiles that were close relatives of dinosaurs, but on a separate evolutionary branch. However, the largest flying dinosaurs, ancient birds from the Mesozoic, achieved impressive dimensions, with some hesperornithiforms reaching lengths of nearly 2 meters, though these were secondarily flightless diving birds rather than active flyers. The largest flying birds of the Mesozoic capable of powered flight probably did not exceed a few kilograms in mass, as the energetic and structural demands of flight impose strict size limits. After the extinction of non-avian dinosaurs, birds eventually evolved much larger flying forms like the Teratorn argentavis, with wingspans exceeding 7 meters, demonstrating that the basic avian body plan was capable of supporting large flying forms once freed from competition with pterosaurs. Fact number 95. The discovery of dinosaur remains in amber represents one of paleontology's most exciting recent developments, with specimens including feathers, skin, and even a complete tail section of a juvenile coelurosaur preserved in 99-million-year-old Burmese amber. These specimens preserve three-dimensional structure and sometimes even color patterns with extraordinary fidelity, offering details impossible to obtain from compression fossils. A feathered tail preserved in amber shows barred color patterns and feather structure similar to modern birds, while isolated feathers display diverse forms including simple filaments, branch structures, and fully modern pennaceous feathers with interlocking barbules, demonstrating the full range of feather diversity existed in the Cretaceous. Fact number 96. The debate over whether Tyrannosaurus rex was primarily a predator or scavenger has largely been resolved in favor of an active hunting lifestyle, though, like all large carnivores, it surely scavenged when opportunities arose. Evidence for active predation includes the powerful locomotor apparatus, suggesting sustained pursuit capabilities, the sophisticated sensory systems needed for tracking and capturing prey, healed bite marks on herbivore bones, indicating attacks survived by prey animals, and the enormous energetic costs of maintaining such a large predator body, which would be difficult to support through unreliable scavenging alone. Modern large predators all hunt actively while also scavenging opportunistically, and Tyrannosaurus likely followed the same strategy, with hunting success rates probably similar to modern large predators. Fact number 97. The arms race between ankylosaurs and large predators produced increasingly sophisticated armor and weapons on one side and increasingly powerful jaws and teeth on the other, with some interactions preserved as bite marks on armored osteoderms. Some ankylosaur armor bears punctures and scratches consistent with tyrannosaur tooth dimensions, indicating these predators attempted to breach the armor of even well-defended prey. Conversely, the tail clubs of advanced ankylosaurs like Ankylosaurus were clearly capable of injuring or killing tyrannosaurs, creating a genuine standoff where the outcome of encounters depended on circumstances. Ankylosaurs were nearly invulnerable when facing their attackers, but vulnerable if flipped onto their backs or attacked from below, while tyrannosaurs risked crippling injuries if they misjudged their approach and came within range of the tail club. Fact number 98. The end Cretaceous extinction eliminated not only non-avian dinosaurs, but approximately 75% of all species on Earth, making it one of the 5 largest mass extinctions in the planet's history. The selectivity of the extinction provides insights into which characteristics promoted survival during extreme environmental stress. Small body size, ability to shelter underground or in water, omnivorous diet, and widespread geographic distribution all correlated with survival. Animals dependent on photosynthesis-based food chains, particularly large herbivores and the predators dependent on them, suffered disproportionately. Marine ecosystems experienced severe disruption, with ammonites, mosasaurs, and plesiosaurs going extinct, while some fish, sharks, and marine reptiles survived. The extinction's selectivity shaped the modern world's fauna as the survivors radiated to fill vacant niches during the Paleogene, creating the mammal-dominated ecosystems familiar today. Fact number 99. The relationship between modern birds and non-avian dinosaurs runs deeper than simple descent, as birds retain the fundamental body plan, skeletal structure, and many behavioral characteristics of their dinosaurian ancestors. Birds still walk digitigrade on their hind limbs with a distinctive dinosaurian ankle joint, possess hollow bones with air sacs, lay hard-shelled eggs, show complex parental care, and, in many species, display elaborate courtship displays. Some birds, particularly ground-dwelling species like cassowaries, show remarkably dinosaurian appearances with their large size, powerful legs armed with dagger-like claws, and aggressive territorial behavior. Understanding that birds are literally a specialized lineage of theropod dinosaurs that survived the end Cretaceous extinction transforms our view of both groups, making dinosaurs not entirely extinct, but merely changed in form, continuing to thrive and diversify into the 10,000 species of modern birds. Fact number 100. The legacy of dinosaurs extends far beyond their direct descendants, as these animals fundamentally shaped the evolution of mammals, which remained relatively small and primarily nocturnal throughout most of the Mesozoic, due to predation pressure and competition from dinosaurs. Only after the extinction of non-avian dinosaurs could mammals exploit diurnal niches and evolve large body sizes, eventually producing the megafauna of the Cenozoic, including elephants, whales, and eventually humans. Without the extinction event that ended the Cretaceous, intelligent mammalian life might never have evolved, leaving Earth dominated by dinosaurs whose descendants might have eventually evolved sophisticated intelligence, creating a world where the dominant intelligent species descended from raptors rather than primates. The history of dinosaurs is thus inseparable from human history. As we exist in ecological space, these remarkable creatures once filled, inhabiting a world still shaped by their extraordinary reign.